The Big Bang Theory doesn't make as much sense now that the James Webb Space Telescope has found new information. The James Webb Space Telescope recently made an amazing discovery that is shaking the field of physics worldwide. With one stunning picture, it ended long-running arguments and left experts speechless. No more guessing. The Webb Space Telescope's most recent discovery is both stunning to look at and a game-changer that could change the way we see the world. What heated argument among experts has this picture finally put an end to? How does the beautiful picture taken by the James Webb Space Telescope change the way we think about the universe? Join us as we delve into the image that ends the physics argument, unveiling the revolutionary discovery made by James Webb. One of the main problems in astrophysics is that scientists can't agree on how old the universe is or how fast it is growing. Scientists of all generations have been puzzled by this unsolved phenomenon, and they are conducting various studies to find answers. Cosmologists try to figure out how the universe was made, how it works, how it has changed over time, and how it will end. In the last 100 years, there has been significant progress in this area. The Big Bang Theory, the most popular theory in cosmology, suggests that the universe has been expanding for about 13.8 billion years, starting out very hot and dense. The Hubble constant, which measures the rate of this expansion, is a critical piece of this puzzle. However, measuring the Hubble constant is not straightforward. There are two main types of measurements for the Hubble constant: local measurements and measurements from the early universe. Local measurements look at objects in space like Cepheid variable stars and type Ia supernovae, which are used as standard candles to measure the Hubble constant. By measuring how the expansion of the universe changes their speeds, astronomers can determine the distance to these objects and calculate the Hubble constant. Early universe measurements involve readings of the cosmic microwave background radiation, CMB. Discovered in the 1960s, the CMB is the afterglow of the Big Bang observed when the universe was just 380,000 years old. By measuring the tiny temperature and polarization ripples in the CMB, astronomers can estimate the age of the universe and its expansion rate. However, there is a problem. These two methods do not give the same results. Findings from local measurements suggest that the universe is expanding faster than the CMB data indicates. Scientists have been working hard to understand why these results differ. The discrepancies imply either undiscovered physics or potential errors in one or both measurement methods. The James Webb Space Telescope has pushed the boundaries of what we can observe, allowing us to see deeper into space than ever before. Its capabilities enable it to reveal elements, planets, and galaxies that were previously unimaginable. Naturally, scientists hope that data from Webb would help them measure the Hubble constant more accurately, but the first wave of data has only complicated matters. The new findings challenge our previous understanding. Could this information lead to a new theory of the universe, altering our perception of how it works? We might need to rethink what we know about space, potentially discovering new particles and forces or reevaluating the role of dark energy, the mysterious force accelerating the universe's expansion. As we continue to uncover new information, our ideas about space evolve. For example, the discovery of the cosmic microwave background radiation in 1965 provided strong evidence for the Big Bang Theory, shifting the belief that the universe would last forever and expand at a constant rate. Similarly, the discovery of the universe's accelerating expansion in the late 1990s introduced the concept of dark energy. Whenever we learn something new, we must reassess our current understanding. The James Webb Space Telescope's recent discoveries are a testament to this ongoing process, urging us to rethink and refine our theories about the universe. We come up with new ways to understand the universe better. If not for these challenges, the problem we're facing in cosmology right now could lead to the discovery of the best ways to understand the universe. Although the problem is difficult, It is also exciting because it pushes us to develop better tools for exploring space. Scientists from all over the world are interested in this cosmological problem because they all want to know more about the universe. The most important thing is that it shows how science is always growing and changing as we learn more about space. The S8 tension is another issue that goes along with the Hubble tension. This tension relates to how matter is spread out in space. Scientists use this to create a structure of the universe and see how it has changed over time, referring to this distribution as lumpiness. Some parts of space have many galaxies clustered together, while others have very few. To determine the extent of this lumpiness, scientists use different methods. One possible approach is to look at how the different densities of massive objects, like galaxy clusters, bend light from distant galaxies, a phenomenon known as gravitational lensing. This allows us to infer the presence of dark matter, which does not emit light and is therefore undetectable directly. Another crucial tool is the cosmic microwave background, CMB, a glow left over from the Big Bang. This light has traveled for about 13.8 billion years, carrying information from the early universe. By analyzing the CMB, scientists can determine how lumpy the universe was at its creation, which should match the current large-scale distribution of matter. However, there's a catch. These numbers don't match up. The lumpiness suggested by the CMB, which follows the non-spherical gravity distribution model, indicates that the early universe's matter distribution was more even than what is observed with gravitational lensing. This discrepancy suggests that there might be something missing in our understanding, possibly related to dark matter. The question of what dark matter really is and how it works remains unanswered. But there is still hope. The James Webb Space Telescope, with its unprecedented sensitivity and clarity, will transform astronomy. It will explore the early universe, uncovering how the first galaxies and stars formed, allowing us to better measure the universe's expansion and matter distribution. To answer these critical questions, we need to observe carefully and potentially develop new theoretical methods. Discovering more about dark energy, learning new physics, or gaining a better understanding of dark matter will have profound effects on many areas of science. Solving the mysteries of the universe is like assembling a complex puzzle while wearing blindfolds. Scientists are like detectives, determined to figure out what's going on. NASA's newest effort, Project Flamingo, demonstrates the agency's growing commitment to scientific exploration. This project is a significant leap forward in computational cosmology, using one of the world's most powerful supercomputers at Durham University in Britain. With more than 50 million computer hours and 30,000 processors, Project Flamingo represents a massive effort to study the entire universe, with a particular focus on dark matter. Dark matter is a strange substance that does not emit, absorb, or reflect light, but is believed to exist because of its gravitational effects on visible matter. Scientists are still puzzled by its elusive nature. Unlike other simulations, Project Flamingo includes a wide range of cosmic phenomena, from stars and black holes at the center of the universe to galaxies with varying gas compositions. The objective of major projects like Project Flamingo is to resolve discrepancies in our understanding of the universe's structure, such as the S8 and Hubble tensions. These differences in measurements highlight gaps in our knowledge and suggest that we do not yet fully understand how the universe works. To understand these metrics better, think of them as types of music, jazz and classical. Each has their own style, but are still interconnected. Project Flamingo aims to unify these different perspectives, helping us all understand the universe better despite its complexity. The cosmic strain remains as humbling proof that many mysteries of the universe are yet to be uncovered. It seems the universe is reluctant to reveal its secrets to us right now. As we gather more data and develop better models, like Flamingo, the set of problems we need to solve grows larger. Each answer we find brings up new questions, making the quest for knowledge never-ending. This shows that our journey to unravel the mysteries of the universe is both complex and ever-changing. In the early 1900s, Edwin Hubble made the groundbreaking discovery that the universe is expanding. Since then, our understanding has grown at an astonishing rate. The Big Bang Theory, dark matter, and dark energy are just a few of the groundbreaking concepts that scientists have uncovered about the universe's size and shape. By studying the cosmic microwave background, CMB, and meticulously mapping the locations and velocities of galaxies, we continually piece together the cosmic puzzle. This constant discovery process motivates us to learn and understand the universe better. The universe is indeed very mysterious, and revealing its truths too quickly might not be advisable. At each stage of their research, scientists pose new questions, revise models, and develop better theories. The Big Bang Theory, once controversial, is now a cornerstone of scientific knowledge. Similarly, dark matter, once a speculative idea, is now a crucial part of our understanding of the universe. Dark energy, discovered in the late 20th century, is now one of the most significant aspects of our comprehension of cosmic expansion. Now, let's delve deeper into the different methods scientists have used to understand the universe's expansion over time. Despite their efforts, some aspects still elude comprehension. In ancient times, people believed that everything in the sky, including the sun, stars, and planets, revolved around the Earth. However, visionaries like Copernicus and Galileo challenged this geocentric view, proposing that the Earth and other planets orbit the sun, a revolutionary perspective at the time. In the 20th century, Einstein introduced a radical new way of thinking about the universe. He proposed a model in which space and time are not separate entities, but a four-dimensional structure called spacetime. His discoveries revealed that the universe is constantly changing. Hubble's observations in 1929 showed that galaxies were moving away from each other, indicating that the universe was expanding. This led to the development of the Big Bang Theory, which posits that the universe started from a very small point and has been expanding ever since. Initially, it was believed that gravity would eventually halt this expansion. However, in the 1990s, astrophysicists made a surprising discovery. The universe is not only expanding but doing so at an accelerating rate. This led to the concept of dark energy, a mysterious force driving this acceleration. The Flamingo Project has become a significant player in cosmology, offering more than just a typical supercomputer exercise. It provides a highly realistic virtual model of the universe, incorporating data from the CMB and galaxy measurements to create a digital representation of the cosmos. The main objective is to determine whether the early universe, based on our current understanding of physics, could naturally evolve into the complex structure we observe today. One unique aspect of Flamingo is its consideration of both dark and light matter in its virtual model. This approach differs from other models that typically overlook light matter. To illustrate, think of analyzing a car's frame, engine, seats, and wheels to understand how this comprehensive method works. By including all components, Flamingo provides a more complete and realistic simulation of the universe. As we continue to explore and understand these cosmic phenomena, our models and theories will evolve, bringing us closer to unraveling the universe's mysteries. Each discovery, like a piece of a complex puzzle, helps us see the bigger picture, driving us to learn more and expand our understanding of the cosmos.